ladies and gentlemen, that time of the evening where we march ahead with our next presentation, and the topic is quite intriguing. Again, it's on magic of algorithms. It's going to be a live coding session using sound data. In fact, in this particular session, we're going to have a live demonstration using sound data. We have with us Mr. Sushant Verma, who's the co-founder of RATLab. Well, welcome there. So yes, are you all set?
Yeah.
Are you all ready? Then let's have a round of cheer and let's welcome our next speaker, Mr. Verma. Over to you.
So thank you very much. I'm going to need a lot of cheers, a lot of clapping, maybe whistles and hooting as well. Yeah, what I'm going to do is something really interesting. All of you are data for me. And you're going to be creating some sound, and we're going to use that, create that data to translate that into some kind of spatial form. So as interesting as it sounds, as complicated as it is, we'll start with a presentation. Can I have the presentation? Okay, something I would like to talk about to start with. Like, we as humans have a tendency, and most of you are designers here, and you would agree with me partially or fully that we have a tendency to chase nature or natural systems. You know, with our limited conscious knowledge, whatever we understand out of nature, it's quite complicated, and our unlimited subconscious being. So there is always a tendency to mimic nature in certain ways, and natural systems are quite interesting. And apart from being an architect, I'm also a computational designer, which again is quite alien to people right now in India. But I'm going to come to that. How does this work? Okay, cool. I'm techie, but these are kind of new gadgets. Okay, anyways, so talking about nature, it's very interesting, and I think most of you would agree. Do you agree with me? You follow nature in some way or the other? Yeah, in your designs, you know, whatever you do. You know, we always look at nature, but there is something very hidden in nature. That is the code behind nature, the algorithms that are hidden around us, and we are surrounded by them. And our human brain doesn't have a tendency to read them more often than others. But let's say, for example, this image, you know, this not only shows a natural system, but the code that is hidden behind the system as well. And nature is about numbers. It's about mathematics. And whenever it comes to mathematics, something that intrigues me most is the data. How we can use that data, how we can code it, how we can decode this data to do something interesting. So, I mean, there is a code of nature, and there is a nature of code as well, to how much capacity as a designer we can understand. Just going to show you a small clipping. It's about two minutes video to demonstrate nature, natural systems, and numbers, and how all of this is interlinked, and how data and mathematics is embedded in natural systems around us. Fibonacci spiral, which continuously grows to evolve new forms in nature. The famous Nautilus spiral, which has a mathematical code behind it and how it's formed. The golden ratio. triangulation system, creating a Voronoi pattern. Yes, so I mean, we've all seen how mathematics is embedded, numbers are embedded in nature, and pretty much all the natural systems. And the beauty of these systems, there is a sense of aesthetics to it. There is a sense of beauty because of the mathematics that is underlying in these processes, and how we can use these to understand nature even more. Now, talking a bit about data, you know what? We are right now in the world of big data. You know, all of us are using Google, Facebook, Twitter. How many of you use hashtags? Can I get a show of hands? Hashtag, who uses hashtags? 1, 2, 3, 4. Many of you use hashtags. And I can bet that 90% of you don't know what hashtags are for. Apart from showing the movement you are in and expressing yourself, it's to collect data, something which we don't know. We all are a part of the data. We all are using Google Maps, and Google is tracking us all the time. It knows its movements, where we are going, where we are sneaking out, pretty much everything. And that data is being used to do something. Now, as designers, why aren't we using this data a little more seriously? Now, data has to be structured and analyzed in a very systematic way. Very recently, I was giving a talk at one of the TEDx forums, and one of my fellow speakers, who happened to be a data scientist, Dr. Angad Chaudhary, I have to quote him because the whole idea came from there, that he actually used the public data of people who express their interest on Facebook to go to a particular forum. And if I could have done that, I mean, unfortunately, I didn't have too much time because FOAID is very packed. If I had got more time, I would have probably done that and shown that to you, the data of each one of you. What all are your public groups, where you are going, who are you interacting with, what are your friends, any information that is public. That can be used and processed to do something interesting. And data comes in hierarchies. There is a lot of complexity to it. And we as designers, when we see cities, we have cities that are I see 3 or 4 typologies of building here. All of that is data. So I have data A, B, C, and D. And I can categorize that to calculate something. We have climatic data around us, which we use. Most of us use that while designing. We have people. All the people are like data. And that's exactly why I said all of you are like data for me. As a computational designer, I see all of you as data. What we can use this data for, how we can use that, is something which can be very interesting. For example, train stations. You have your time charts, your departure schedules at the airport. That's a live example of a data visualization happening in real time. And it's very, very complicated, more than we can imagine. There's a lot of computing happening. Algorithms calculate how much time the metro is going to take to come to the next station. The algorithms will calculate how much time should be given to a traffic signal, whether it has to be green for 20 seconds or 30 seconds based on traffic movement. These are complex processes. And we can use data to visualize anything. The interesting part right now for this particular forum is music. I'm going to take sound as a data. And we're going to create sound. And sound visualization is something which most of us have seen. We had these music players, Winamp or Sonic. I don't know, people from late 80s or 90s, maybe able to recall, where we can use to visualize music. What we see behind a DJ, music being coded into a visualization. These are some examples of visualizations. Now, all of that is based on some kind of data, which is sound right now. And one of the German authors very nicely quoted, music is liquid architecture, and architecture is frozen music. So can we really capture this music in time and use that to create something slightly more interesting, perhaps something like this? Can we spatially transform data into something else? So I'm going to try to do that. I'm going to code, I'm going to create some music. I don't have a guitar, I don't have drums here, and I'm not a musician actually, but this is my tool, my laptop and my coding engine. And I'm going to create some music. And if you see, there's an algorithm running right now. which is actually taking my data. My voice modulation is actually being recorded over there. And a lot of data is being translated to do something. So I'm going to create some music, some sound. I don't know if it's going to be pleasing or not. But yeah, that's my coding engine. And I have a code on the left-hand side. And I have visual on the right-hand side. You can see there is sound being coming out. Now there is a code running. The code is actually making the music. And I have certain parameters in this code which I can alter, which I can change to let the output change and the music will change. For example, let's so it gave a syntax error. Now I have reverberation here, I have a flanger, I have an echo effect, I can change that. I'm adding new parameters, not really pleasing, but you've got some very nice music system, by the way. I didn't know the intensity of this. But if I increase the amplitude, I increase the rate. These are certain parameters. As I said, I'm not a musician. I won't have like only partial knowledge of all of this. And on the right-hand side, what you see is the music being visualized, the sound data being translated into this graph, which is continuously moving in real time. And that is what the potentials of data are. So I can go on to create any sort of music, pleasant or unpleasant. Don't judge me on the music that is coming out, but the idea is to show what a code can possibly do, what an algorithm can possibly do. And that's like a modified algorithm which I'm using to create data. And the same data is running in my design engine as well. So this is software which I use to design anything right from buildings to cities. And that is also taking data in real time. And that graph shows the input. So my microphone has turned into a sensor which is taking all this data. And whatever I'm saying here is being translated here. So I have the wave pressure from the left channel, from the right channel, continuously being updated. And I have a very low memory software. It's not like it has like a super high RAM or something. It's a very simple algorithm that doesn't use much of a memory. Now let's see what we can, how else can we start to visualize this data in Grasshopper, which is a tool which I'm using here. So I see music being visualized in real time, and whatever I'm saying is kind of pumping up the beats slightly. The frequencies and amplitude are taken as inputs, and a form is being created. And this form are actually just simple curves which we can draw. And instead of drawing a curve, we're actually using data to create a form, which can possibly be converted to something else as well. If I change the sound, for example, so this is actually what we see on the music players as well. It's using an algorithm and converting it in real time. Now let's see how we can transform that spatially into something else. Okay, let's get the next algorithm. And so here I have data translated in a different method altogether. I've actually transformed the simple waves into a circular data, more organic. And it's creating a form. Now if I pump down the volume, it's going to create slightly subtle forms. It's not 100% predictable what I'm creating. And I'm not advocating this is how you should design, but it's to show the power of algorithms and how we can use something as simple as sound data to create a form which is slightly more complex than what we can design otherwise. And if I have to just so that's my visual algorithm. The way I was writing the other algorithm, this is more of a visual used by designers. So let's say I've paused the music, I've paused the data recording. Now it's not recording any data, and the data is static. I've got a set of curves in my design software. It's a 3D modeling software. And I've got these set of curves, and these curves represent some kind of data. And they have some kind of information. And every color that you see here is also having some information. And as a designer, I'm in total control of these values, of all of these numbers. What is the length of each line? What is the angular curvature of these curves? And how we can possibly use them to create something else. Let's say we can create a form, a series of forms we created using the sound data, which is more like a design, like it's kind of sectioned in a certain way to create this morphology, which is formed by the sound data. Something like this, for example. This is another sound. So let's record this data again. And try to get some sound from you guys. So can you give me some sound data? Can you, I don't know if, maybe you can clap. That's one way of doing it. So there's sound data, it's being recorded, and I'm using this microphone which is actually translating the data. And any musician here by any chance? Yeah? Can I have you on stage? What do you play? Yeah, perfect. I'll give you 15 seconds only. Sorry, that's the window I can give you. I'm tight on time as well.
Sa re ga ma pa da ni sa sa ni da pa मगरे सा दान दान मूरत कृष्ण मुरारी दान दान मूरत कृष्ण मुरारी.
Perfect. Great. Thank you so much. That's a round of applause. What's your name?
शशांक अग्रवाल.
Thank you. So, okay, so we have Shashank's sound here, which is being recorded. And I'm going to convert that into some series of curves. I'll probably 3D print that and give it to you later. Yeah. So that's the power of algorithms, what we can possibly do. And let's look at another system here. Another method. Let's say we translate the data to do something else, to create another kind of spatial form. I'll just slightly toggle my data. I need to switch off certain codes in the algorithm and switch on certain others. Yeah, there you go. Here you see the sound is again translated into a spatial form. So you have like series of blocks. It's a grid of 20 by 10. You have a surface which is being curved. And the curvilinearity of the surface is coming from my sound, my data, right now. So if more sound I play, more kind of different results it'll give me. At certain scales, it is difficult to really understand how the data is being translated. But again, since I have the whole list of frequencies and amplitude, and I'm translating that linear data into a two-dimensional data here, which is giving me a three-dimensional form. And as I'm talking as well, it's taking that data, increasing those frequencies, and the peaks are getting higher. And let's say I log the data. I stop recording the data. So the music is on, data has stopped. I'm going to put the volume down. A form is being created here, which I can see. And there is a very interesting curve which we have. I'm just going to bake this geometry and get that to my modeling software. Yeah, so there you go. So this surface is being created using the sound. So whatever I'm saying, whatever I'm speaking is being converted into this kind of a morphology. And that is just one potentials which one can have. I can just quickly show you a series of other forms and morphologies, which actually was done at 3 a.m. last night while I was preparing the script. So you have like 3 sets of data. One is like more of a silent music. Then we have slightly louder music. Then we have more of an R&B, which had more sounds and multiple kind of frequencies coming into play. And there's other sort of data as well. Such as this. I've translated that into various kind of forms. Now these can be buildings as well, by the way. That's not essentially how we design, but we do design using data. And I'm going to show you a glimpse of that afterwards. So like this is a digrid system being created. And if you start to look at these forms slightly more carefully, you know, there is slight linkage to nature and natural forms and natural systems, what we see. And like this is more like a fractal pattern which was being formed using a digrid system from the sound waves. And then there's a hexagonal system as well. So various kind of morphologies being kind of embedded into these systems and forms using sound data solely. Okay, can I have a presentation? Now here we were talking about translating data. So just going to wrap it up by showing you a glimpse of how we are converting data and what kind of data we are using. Just to give you a background, a few images and glimpses. Like this is population data of Tokyo. This is population data and density of Delhi. Now you can understand a lot more, but just by looking at the visualizations. You don't need the numbers anymore. So data can be used to visualize something which is slightly more complex to understand. And how we do at RAT Lab, which is the organization I run, is how we operate on data and use that at various scales. So just segmented, very quick glimpse of works at small, medium, large, and extra large scales. Product scale, architectural facade, urban scale, and what we are doing at various scales using data. And I can bet after looking at these things, now you can kind of relate to the natural systems and forms that you see around you, and which is what we use and deeply embed in our work as well. Like this is a bench. It's a fluid bench sectioned in a certain way to more like a natural pattern. Some kind of artwork being created, again using data. And if we are using data to create something, we have the control of how to use that data, how to fabricate that. This is an installation we did I think last year or last to last year. And the image on the left you see is the skin of a coral. And that's a natural system. Nobody asked nature to design hexagons like that. Nobody asked nature to drive the mathematics in that way. But that's how structures are formed. That's the whole morphogenesis of systems and form. But there is a lot more that goes behind instead of just translating that data into something, some kind of substantial form. There is a bit of science that goes behind. Like that environmental analysis shows the radiation on every face. So these are hexagons. There were about 9,000 surfaces, hexagons, which is into 6, about 5,300 surfaces. And all of them were analyzed with respect to the solar angle at a particular time. So if you start to calculate that, 5,000 and the solar angle, calculate that data, it's going to take a lot of time. But algorithm helps us do that much more quicker. So while we are designing it, we can actually do some kind of analysis as well. This is again an installation which we put in one of the malls in Noida. Now this is how fractals happen, how things become faceted in nature. And taking inspiration from that, we've created this interior space, which is used on a subdivision method. And we use a subdivision method to not just design this, but to control the construction process as well. So we didn't require any working drawings to create this kind of a wall system. We required a point cloud system. And we had to actually teach a local guy, a local carpenter, how to read that data. And once he read that, it was so quick to make this. These are a few images. And that image on the top right you see is of a marble which is CNC cut, facets, again through an algorithm. And once the algorithm is ready, it takes a few seconds to create these geometries. A building facade which we are finishing in Gurgaon. So this, we have moved on to a slightly larger scale. All the facets are again analyzed. The cost was the major parameter in this project. And we really cut down the cost to half using an algorithm and design it environmentally. At an urban scale, this is a project in Shimla which we facilitated on, in which we used the natural flow of water as an algorithm to understand where the system is going to kind of allow water to flow. Like this is a video. And in terms of data, somebody who understands Cartesian system and mathematics, there is a point cloud system. Each point has an x, y, and z value. The z value is taken. It calculates the z value of all the neighbors. Whatever is the highest, it flows there. So simple logic. So water will automatically flow to a slope which is in that angle. So we don't have to calculate slopes. Instead, we write the algorithm which shows us how water is going to flow. Presentation. Yeah. So that's just a glimpse of things, what we've been doing, again, at SML-XL scales, and how these natural systems, algorithms, data are scalable. And if you see that in nature as well, the wing of a dragonfly is very similar to the pattern of a tornado which is happening. And that's the whole beauty of nature, that everything comes down to algorithms, codes, and mathematics. So use that code, use those numbers to create something, and create that to create better designs, I would say. And if you don't know how to do that, you can get in touch with us. Thank you.